This month's long answer question is focusing on intermolecular forces, a really common topic for longer answer questions at A level. So let's take a moment to have a look at the question. We've got a graph of boiling points of hydrogen halides, and we're asked to explain the pattern in boiling points in relation to bonding, structure, and intermolecular forces in the four compounds. So let's think for a moment about how these 6 marks might be broken down. We need to identify the type of bonding and the structure and the intermolecular forces present in the compounds. But as well as that, we need to use that to explain 2 things about the graph. There are 2 things we can see here. One is the high boiling point of HF, and the other one is this very clear trend in boiling point from HCl to HI. So there are 3 parts of the question really that we need to consider. Identifying the bonding structure and intermolecular forces that are present, and then using them to explain these 2 key features of the graph. So let's start with identifying the bonding and structure. The question is talking about intermolecular forces present in these compounds. So straight away we know that all the compounds, the hydrogen halides, or hopefully we do know this, are covalent molecular substances. Covalent molecules, simple covalent molecules, however you want to say it. So that has identified both the bonding, which is covalent, and the structure, which is molecular, i.e. not giant covalent. Now that we've identified it as being a simple covalent molecule, we now want to focus only on talking about intermolecular forces, and we never want to refer to those covalent bonds again. So covalent bond strength, the bonds between H and F or between H and Cl, are completely irrelevant when we're comparing boiling points for simple covalent compounds. It's the strength of attractions between the molecules that is important, not the strength of the bond between the atoms in the molecule like the HF. So first thing we're going to identify is that HF has hydrogen bonding. We know this because fluorine is the most electronegative element. It's in the top right of the periodic table. We get hydrogen bonding for any compound where there is a hydrogen attached to either a fluorine or its 2 neighbouring elements, oxygen and nitrogen. So we need to state what's important about hydrogen bonding. So hydrogen bonding is the strongest intermolecular force. By saying this, it saves us a bit of time. So you could say, we could talk about the other forces in the other molecules, the permanent dipoles and the London forces, and we are going to talk about those in a moment. And we could say that hydrogen bonding is stronger than both of those. But by saying it's the strongest intermolecular force, I'm just going to fix my grammar, then you're saying all of that. You're clearly stating. And then we're going to link force to energy. So it takes a lot of energy to overcome that force or attraction, and therefore HF has the highest boiling point. So far we have identified that they are all covalent and molecular. That would give us the 1 mark. We've identified that hydrogen fluoride has hydrogen bonding for another mark, and then we have identified that hydrogen bonding is strong, takes a lot of energy to overcome, and that's why it has the high boiling point. So we're about 3 marks in, and that's where some people might just sort of get a bit, just leave it there really and ignore the rest of the graph. But the rest of the graph is also important to talk about because it says explain the pattern, and so far all we've done is explain the outlier which is hydrogen fluoride. So now we need to consider the trend in boiling points from HCl to HI. And one thing that we can see is that this is a very almost linear increase in boiling points. Before we get to that, we should identify the intermolecular forces present. There's no hydrogen bonding present because you're never going to get hydrogen bonding unless you've got an element that's in period 2, and these are all further down the group. So they do, however, all have permanent dipole, can't spell today, attractions. It's really important that you put the word permanent in. Lots of people just say dipoles, they just go dipole, dipole, and they don't put the word permanent. Every single intermolecular force is a dipole. Hydrogen bonding is formed from dipoles. London forces are temporary dipoles. So you cannot just say dipole on its own. They have permanent dipole attractions and they also have London forces. Depending on your exam board, you might know London forces as van der Waals forces, or you might even know them as instantaneous induced dipoles. I'm going to use London forces because it's just quicker to say and write. So whenever you see a clear trend in boiling points like this one, it is going to be related to the size of the molecule going up. Permanent dipoles are stronger than London forces, but when you look at HCl, HBr and HI, there's a big difference in the number of electrons when we go down the group. So our explanation for this gradual increase is that as you go down the group from HCl to HI, the size of the molecules increases. Now, how does this relate to London forces? London forces are caused by the random movement of electrons causing these instantaneous or temporary dipoles. So we want to link it to the number of electrons. Don't start talking about mass of molecules. That's completely irrelevant. They're too small to be really affected by gravitational fields. So the size of molecules increases. That means there are more electrons and therefore stronger London forces. We can add in, therefore we need more energy to overcome and higher boiling point as we go down that group from one compound to the other. So we've now managed to get 6 marks. We really do need to go in a bit more detail and link the size of the molecule to the strength of the London forces as we're going from one molecule to the next. And because it talked about in relation to intermolecular forces present, we want to be clear about both the forces that are present, permanent dipole attractions and London forces. Just as a last point, this type of question, so it's really commonly asked about the hydrides of group 7, but it could just as easily apply to group 6 and 5, as you can see from this graph. So water and ammonia, as well as HF, all have hydrogen bonding. So you can see the same pattern where these molecules have much higher boiling points compared to the hydrides of the rest of their group, either group 5 or group 6. And then you get the same trend as you go down the rest of the group, a gradual increase in boiling points, and that is the same reason. It's a increased London forces because the size of the molecules increases and they have more electrons. If we compare that with the hydrogen compounds of group 4, what we can see is down here methane does not have hydrogen bonding. In fact, methane does not even have permanent dipoles. None of the group 4 hydrides would, because they're all going to be tetrahedral molecules. And so therefore they're all just going to have London forces, and you're going to have a much more linear trend. Again, due to the increased strength of the London forces, more electrons as you go down the group.